you people.
Yes.
Yes, thank you. Thank you. So I put a title, a basic title. We have many solutions now. This is, of course, a picture of what Bijumam was describing, my brainchild, actually. We initiated this 7 years back, and the project has successfully completed more than 6 years, reaching 7 years now, wonderfully generating about 8,000 units per day. We have successful implementation of this project. At the same time, we have integrated a solar resource assessment there, funded by Government of India. So it's a blend of academic and industrial projects. We are getting revenue. At the same time, we are learning a lot. A lot of studies. I could publish papers on this. So it's very important that we learn a lot based on installations, which will give us strength to go ahead further on this, experimenting further and finding the limitations and pluses and negatives, so that we can correct it when we do the other projects. So I will just start with a recent picture from IEEE, shared by IEEE President-elect and IEEE Life Fellow Thomas Collin. Space-based solar power, a future source of energy. We heard a lot about that. See, the advantage is we have days and nights. We won't get energy during night. Of course, the limitation is that's why we are using battery power to store it. Even in grid scale battery solutions, we need battery for peak shifting and utilizing that power during the peak hours. I think all the students know about solar power. It produces during the day. Of course, it is not dispatchable kind of power. So generally, we use solar energy, and we can very good blend it with the base loads like hydroelectric power stations, because these are modular in nature. I guess understand about that. Modular means you have different kind of generators there in hydroelectric power stations. So all these small generators or bigger generators, we can individually shut down and keep that water there and keep the water level. The issue, that scarcity of water we are facing now in Kerala. It is in the newspapers. We have issues actually. For example, we about 50 or 60% lesser than the previous years of rain. In August, it was more than 80% lesser rain happened. So for the last 3-4 years, it is August, we are getting very good rain. So it's a problem. It's a big issue. So keeping water level is an important thing. So if you have battery storage, bigger grid scale battery storage, you can keep that water. We can store it in battery, and if you have a floating solar power plant in that same reservoir where we have the hydroelectric power station, we can generate power during the day and keep it in the battery, and you can use it in the peak hours. So why I'm telling is this example. You don't have batteries for the general solar power, grid-connected solar power plants. For space-based systems, you have continuous power. If you can transmit that energy to the earth, that will be amazing. So a lot of experience, a lot of national governments are investing on that. So investigate on it, learn a lot on it. You can get a lot of news about this. And of course, renewables are becoming very important. As you know, it will be increasing as per the statistics, as Statista indicated. from 28% of renewables into 38% in 2027. It is predicted like that. It will be even more. And look at the transition. Transition is happening rapidly. You can see how renewables are overtaking the non-renewables. The blue is indicated by the renewables, and the ash is indicated by non-renewables. And of course, this is very important. Why? Because renewables are very important because we need to power 733 million people, about 1 billion people around the world, which are where there is no access to conventional electricity. Conventional electricity is very important for your well-being. That's why United Nations has adopted the Sustainable Development Goals, and the 7th goal is clean and affordable energy. It should be clean and affordable. It is required for removing your energy poverty. So these are the basics that we have to learn when we learn more into solar systems. So I'll slowly jump into the simple solar power plants and all. Just before that, you have to learn that why we are learning solar power plants. What is the importance of solar power plants? Of course, it is very important for removing the energy poverty. The poverty eradication is the first SDG, first Sustainable Development Goal. You might have heard of Sustainable Development Goals. The first being eradication of poverty. Energy poverty is the lack of access to modern energy services. It indicates the wellness of people. If you have energy, then it indicates your developmental. It's actually a developmental initiative, a developmental indicator. So more than 80% of these people who do not have access to the conventional electricity, more than 733 million people, around 1 billion people are residing in sub-Saharan Africa and some of the Asian countries. In India also, we have a lot of unelectrified revenue villages in UP, Bihar, Chhattisgarh and all. So it's important that we can accelerate or we can deploy energy. We can give them power with renewables than the conventional power. It's very easy. It's modular. You can immediately bring power to that area to make the empowerment. It's very simple. Coming back to Kerala, see, the daily electricity consumption has crossed more than 100 million units. So it became record in April this year, 103.5 million units. Because of the soaring heat and a lot of ACs now working. So it's very challenging for a state which have only 30% of power being generated and 70%, around 70% is being imported. So that challenge, of course, I believe that we can meet it with the renewables. So having said that, I will just start my topic. I hope I am audible. Can anyone confirm again?
Sure, you are audible.
Okay. Okay. So when we speak about solar power, a lot of solutions is available now. See, I remember the days when I joined ANERT, I was posted in Wayanad, Mananthavadi. Mananthavadi, we had an office. So Wayanad being a remote or a kind of a backward district at that point of time, I won't say it is backward now. At that point of time, there were a lot of pockets or tribal hamlets where there was no electricity. So we were very busy installing solar street lights, solar home systems in tribal hamlets. That was in 1990. So as a project engineer in charge of the district, our target was installing or finding tribal hamlets in and around the district, finding suitable solutions from solar PV. Basically, we wired up these houses with the solar home systems and solar street light system. We never used solar power plants. So at that time, the inverter technology was building up, or in the beginning stage. So we were installing solar home systems, DC systems, and solar street lights. Mostly solar street lights. We ourselves doing it. I remember the days when we trek 10 to 25 kilometers, 10 to 20, 15 kilometers to the tribal colonies, find some place in between the hamlets. There will be an open place where we will install streetlights. We ourselves will dig the soil and we construct the platform, footing. We wire up ourselves. There were no EPCs available, no engineering, procurement, construction companies available, as we have now. We have a lot of solar EPC companies or developers now. When we give work order to them, they are ready to install it. At that time, we were the EPCs. So we were directly wiring up. We were directly transporting these materials. We were directly connecting all this stuff. So it was tremendous experience. I remember I myself, as a project engineer, installed more than 100 streetlights in the first phase in and around the tribal colonies of Wayanad. So our first experiment was in Pulpalli area at Pakam tribal colony, where I don't have the picture in this slide, where we installed a first sort of off-grid solar power plant with a kind of with a centralized system and distributing it to the houses. That we did without an inverter. We used DC only. So we had an issue like when we connect different houses in series, what will happen is, of course, the last house will lose the power first, then the other one, and finally the beginning of the string will have the power. Of course, there will be a lot of DC drop. So I'm just remembering what we did in the beginning. All were DC systems because the inverters was being developed at that time. Good inverters were not available in the market as well. Okay. Now the technology is being matured, solutions are matured. I think the students attending here very well know about off-grid power plants and on-grid power plants. That is my first line. Solar rooftop power plants. We have different solutions. We have on-grid plants, we have off-grid plants, we have hybrid PV rooftop plants. Recently, we have installed a hybrid rooftop. It's not a roof. It's actually a rooftop plant for Ponmuti hill station, powering the Golden Peak Resort. So we have a 12 kilowatt solar hybrid power plant there, and we have an off-grid power plant also. It's using wind energy also. So rooftop power plants are very popular because you have rooftops available without shade. We can have on-grid power plants, off-grid power plants, and hybrid power plants, and different business model. One is captive, another is RESCO. Captive means the capital investment by the owner, and RESCO means it's a kind of the developer will install the plant, and there will be revenue sharing in between the developer and the owner. So just understand in that way now. RESCO is a kind of model where there will be revenue sharing. Even the installation cost sharing is also there. KCB started with that kind of RESCO plants, but the more attraction came for the captive power plants, where the owner himself invests in solar power plants. Okay. Off-grid were very popular. Now we were utilizing a lot of off-grid power plants. Why? Because that time the on-grid was not so mature in India. So the government of India was promoting a lot of off-grid power plants. We installed a lot of off-grid power plants in hospitals, in government institutions with battery. The only problem is after 5-6 years, you have to replace the battery. And how you are going to do that? So there should be an institutional mechanism if you go for a government organization to replace the battery. Otherwise, after 5 years, nothing will happen. This won't work. But in the case of grid-connected plants, we don't need battery, as all of you know. It will work as per the design life. It will work for 25 years. Okay. Then, of course, the ground-mounted, just like what we explained about Kudalmandam power plant. I have some few slides on that. Kudalmandam power plant in Palakkad, it is a ground-mounted power plant. So generally, we install ground-mounted power plants in non-agricultural areas. Why we did do that? Because of it's very we have to be very selective in finding locations for ground-mounted power plants. That's why we don't have much land for ground-mounted power plants. We have a limitation of space. Only wasteland we can implement this kind of projects. But of course, we have what you call abandoned quarry areas. Some areas where it's kind of we cannot install floating in that area, but kind of marshy land where we can go for this. But still a lot of potential available for ground-mounted projects. And the storage, I already explained. The storage started with our off-grid systems. We will design our battery based upon our usage. We can have 6 hours backup that we call it as one-day autonomy. That with a one-day storage, we can run the plant for 6 hours. We call it as 6-hour autonomy or one-day autonomy based on the definition of MNRE, Ministry of New and Renewable Energy. So ANERT, ANERT being the state nodal agency implementing solar projects, now also with the KCB. We have been doing all the solar projects up to 2015. Then the grid-connected solar projects we are sharing with the KCB, of course. So the initial all off-grid power plants were installed with the battery storages. This autonomy means if you have 6 hours, we call it as one-day autonomy according to MNRE, Minister of New and Renewable Energy. That is the ministry. I think you know about these introductions. And that being the state nodal agency, we have a lot of support from the central ministry. The central ministry is called Ministry of New and Renewable Energy, MNRE. Earlier it was the Department for Non-Conventional Energy Sources. Then it became the name MNES, Ministry of Non-Conventional Energy Sources. That non-conventional term is now changed to renewable energy. So Ministry of New and Renewable Energy. That is the new ministry's name. So under the ministry, we have only one state nodal agency for renewables. It is, of course, it is ANERT. ANERT has a legacy of installing solar power plants for the last several years, the last 3 decades. So I told you that all the off-grid power plants will have a single-day autonomy. If you go for installing, I remember the days in 90s, I installed off-grid solar power plants, later part of 90s in tribal settlements, where we designed the solar power plants with more than 3-day autonomy. So single-day autonomy you do in urban areas where you can attend the battery. But where there is you don't have access to a remote place, there is chance that there will be continued rain and you won't get sunlight for 2-3 days. So there we will design solar power plants with the 3-day autonomy. I remember the days in the initial 2003 solar village electrification which was fortunately headed by me. We had around 12 solar microgrids I remember I used the Siemens manual for designing all the solar power plants. I put the number as 3-day autonomy. That means 3 into the single autonomy of battery capacity. So why we do this to accommodate more solar power in remote areas where we cannot attend easily. It cannot. We don't want this to be drained easily. So that is offset power plants. But in utility scale power plants, utility scale means megawatt scale power plant, just like the Kudalmandam power plant. The lot of projects are coming up with the battery storage, lithium perophosphate or advanced lithium storage batteries are used for storage purpose. We call it as battery energy storage systems, BESS. So all of you know about it. So BESS is an important topic. A lot of solutions are there. A lot of utility scale power plants being installed. In that perspective, you have a lot of installations in California. You have a lot of installations in Hawaii. You have a lot of installations in South Australia. Now, a lot of installations are coming up in India as well. So the next option will be floating solar. The option which is very potential for Kerala, because we have a lot of water bodies around. I will explain those points later. And you have a lot of innovative projects like agri photovoltaics, where you can have both agriculture and PV together. In fact, we have a model project in Palakkad in a society, agricultural society, where we installed in a kind of elevated structures where underneath we have plantations. So in fact, we are doing an experiment on an adjacent area without this kind of solar panel, and this area with the solar panels in elevated structures. We are just comparing how the crop is performing. So these are all research areas we can do. Then highway rooftop is another very important area. I think I remember I guided a civil BTech student, a group of students on this. They presented for their BTech project. It's more structural challenging because solar technology is available. We know about it. So how the structures can be made in a high, like elevated structure where the transportation can be easily done without any kind of blockings. So highway rooftop is a canal rooftop. I prefer highway rooftop in Kerala. If you have some straight highways like the Thrissur, Palakkad, there are areas where you have more than 4 kilometers in a straight stretch. If you have a substation nearby, it's a very important area we can look into. And of course, I already explained about microgrids. I have a picture here, a microgrid installed by my team back in 2000. Okay. So when we speak about solar power plants,
just one point. You said about the highway rooftop.
Yes.
So when you are trying to do that, we are planning to have a panel on top of similar to our lamp posts, right?
Yes, of course. Yes, of course. Only thing is, there the challenges will be like the trucks will be coming up. So you have that much of elevation. And the another thing is how you are arranging to clean the PV modules. So you have to have some walkways built in definite intervals. In that BTech project, we designed like that, and you can have a very good. In fact, I request all the students here to look into that. Design a highway rooftop plant. It's a very, 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 very attractive project for Kerala. See, the important thing is if you have a substation nearby, if you can have a very small substation, maybe a 33 kV substation there, in the vicinity you can go for this so that you can immediately evacuate it. So, and another important thing is like you don't have a central inverters needed, teacher. So that is attraction. You can have distributed. For example, in Kudalmandam, I have a Hitachi 1 megawatt each. Currently, I did the AMC for it. I arranged the AMC Hitachi people. They came there and they after the 7 years of continuous running, it's continuously running. So it's very important that you have the AMC in place. If there is a surprise, then it will cost more than 30 lakhs. So it's important that, so that's why I could learn that a lot of people are now going for distributed. So you have kind of 100 kilowatt inverters or 50 kilowatt inverters, string inverters deployed in this highway rooftop. Even lesser than.
Is it existing anywhere in
Yeah, it's
India?
existing. Actually, internationally now Germany has signed an agreement with a corporation. They are aggressively moving in that, and France has already done some projects.
Because already what happens is our highways are fully now, it's hot. There are no trees in the mid because the construction is going on. So I think this can be easily implemented.
Easily implemented, and you don't have shade. You don't have
Correct.
shade. You have to have a structure. It's pretty good investment than the offshore wind.
Correct.
Because you need to multiply your.
Yeah, the students can think of having some projects being designed in their area itself.
Yeah, exactly. So I request all the students, so the upcoming scientists and engineers. So these are the projects that you can take up in your MTech, BTech projects. I graded for a civil guy, so I asked all the civil, there are civil structural simulations we used for making the safety of that structure. So they were looking at that only. I just, they approached me to see that how the system looks like. So you can have a civil teacher or a professor.
Yeah, you can always, now it is interdisciplinary, more or less.
Yeah, exactly. So, so thank you, teacher. So, see, whenever we speak about solar power plants, this kind of comes to our mind. 40 megawatt capacity, the world's the biggest 100% solar powered airport. Now, a lot of solar powered airports are there in the world. My colleague, Dr. Srinath from same university, Malaysia, Pahang, he did his PhD in solar airports only. He's currently doing his postdoc in Europe. During his PhD, he published 14 papers. And out of that, 10 papers from the SCI journals. So it's very important stuff. So what CL has done is amazing thing. So they are actually experimenting. They started the huge rooftop of 1 megawatt on their rooftop, and they started with the installations. I remember the days when I was doing the material inspection for the first 14 megawatt phase. I was actually moving around that area with Satish. He's currently, I think, he's there only. I think Satish has come to our Green Technology Symposium for a presentation. So, it is an amazing experiment that with all the challenges, you can install a huge power plant in an airport. So they have shown it to the world, and it's a kind of they are meeting their needs with their own generation, and they experimented with the 2 tiny photovoltaic floating solar power plants. You can see the pictures here. That comes to a total of 450 kilowatt each. Okay. So if you look at, I give these examples to give you a kind of to trigger up to understand that what exactly happening around the world and around the country. So these are the huge power plants, huge utility scale power plants, megawatt scale power plants in our country. Fatla Solar Park in Rajasthan, Pavagada. I was fortunate to visit this Fatla and Pavagada. Kurnool in Andhra Pradesh, and GNP Kunda, Andhra Pradesh, there is 1,500. Reva is ultra mega, 750 megawatt. It's a single kind of installation, a single stretch installation, I should say. It's not different parts joined together. It's a single huge installation. You have Charanka. Charanka, in fact, I walked. I was part of the Charanka Solar Park when I was leave from ANERT in 2011, 2013. I had a contribution to Charanka Solar Park, a 25 megawatt we installed with Wipro Eco Energy. I was the consultant there. I remember the hot days in Kutch. It was in Kutch. So there we used thin film solar PV modules. It was amorphous with single crystalline silicon tandem junction solar PV modules. So Kamuthi near Ramanathapuram is very important to us. Now, if you happen to be around Ramanathapuram, you can visit these plants. Let me know if you people are visiting Kamuthi. I have people, some of my friends from that Adani Power. We can arrange the visit, no problem. So it's a huge power plant in Tamil Nadu near to us. Okay. So coming to some theory, we have a lot of solar irradiance coming up. These three are that you have to learn: direct normal irradiance, the components, diffused horizontal irradiance, and DHI and GHI, global horizontal irradiance. So for direct normal irradiance, the name indicates it's direct solar radiation falling to the earth. So if you want to install solar thermal power plants, you would need DNI, higher DNI. So you have Rajasthan, state can have this kind of we call it a CSP, concentrated solar power. Diffused horizontal radiation is, of course, if you have a lot of clouds like Kerala, of course we will have the reflected from cloud. That is also adding to our solar power generation or giving benefits to the generation where we are getting radiation. So GHI is actually a sum of DNI and DHI. So direct normal radiation plus diffused horizontal radiation gives your solar horizontal radiance. There are different models you can calculate GHI, and you can convert to how it will be. What will be the equivalent generation when to the inclined surface? You go for simulating in different software solutions like the PV Sol, Red Screen, stuff like that, or SAM. Then you are putting a number of irradiation, which is global tilted irradiation, GTI. Just note the point, GTI. Global tilted irradiation is not global horizontal radiation. You can arrive a GTI from GHI. In fact, I used a model. I developed a model for my PhD to find out the GTI from GHI. So, because GTI, global tilted radiation, we need to know to predict or to put into some calculations. Okay. Anyway, for students, just remember DNI, DHI, that is diffused horizontal irradiations, and GHI, global horizontal irradiation. We have pretty good solar irradiation, GHI, around 5.5 kilowatt hour per meter square per day. Look at the units, like kilowatt hour per meter square per day. And if you multiply with the 365, it comes around 2000 kilowatt hour per meter square a day, which is average. The state of Kerala having more than 300 sunny days. If you look at Kerala, you have six months, you have pretty good insolation, and 6 months you have rain. So starting from December, January, February, March, April, up to May, you have good insolation. We don't have a kind of extreme winter. So we can count December also as a month which is having a higher generation. And from June onwards, you have issues. From mid-May, you will have rain. So of course, these patterns are completely changing. We cannot predict now because of the climate change. Okay. I took this from the Mitivanam data, satellite data. You have pretty good insulation. If you look at DNI, it's very low, 4.5 average. But if you look at GHI, you have good insulation. Just compare that in Stockholm, Sweden, you have just above 3 kilowatt hour per meter square per day. Then you can understand that how we are benefited when compared to the Scandinavian countries. I think you follow me. Please interrupt me because I'll be speaking on different subjects and terms, terminologies. So this is not an offline class, so kindly interrupt and ask me what is the meaning of that particular term and stuff like that. So please remind me or alert me. You can just unmute and ask questions. So type of solar power systems, I just introduced standalone PV systems or off-grid solar systems with batteries. Grid-connected PV systems, all of you know about that. It will be connected to the grid, your distribution grid, and of course, it will be your power will be evacuated through your service wires to the grid, local grid, and it will be, for example, evacuated to in a utility scale power plant like Kudalmandam power plant. It will be evacuated to a 11 kV line or 33 kV line based on the availability of KCB's line. In hybrid PV systems, of course, you will have a battery backup as well, along with a grid connected system. So hybrid PV system will have a hybrid inverter. I'm just stressing that name, hybrid PV. It is not hybrid renewable energy system. Hybrid system means generally meant to say you have different resources together clubbing to a grid to form a local grid. Like wind will be there, solar will be there, battery will be there, and there will be fossil waste sources like diesel. It's called hybrid systems. So hybrid PV is different. Hybrid PV is you have a hybrid inverter. It's PV only. Of course, you can have battery. Of course, battery will be there, where you can have an islanding system. In grid connected, you don't have an islanding system. You don't have battery. But in hybrid PV systems, you have an islanding system where battery will be also connected based on your your requirement. There will be some capacity battery based on your critical load applications. So whenever the grid goes, it will island and power your grid, power your local grid. So grid connected system, I think most of the students here can understand how a grid connected system works. You can see solar panels here. From solar panel it comes to a junction box, a DC-DB. Then of course, this all will be like this all will be together with a DC-DB. Like you have a solar isolator or DC isolator, and you have a you will be fuse unit, SFC, SFU. You have a fuse unit. You have a DC isolator, and you have an SPD. SPD is surge protection device. All this stuff will be together in a DC-DB. Okay, I'll repeat. You have DC cables coming up from the strings from the solar panel, arranged coming to the DC junction box. This DC junction box will have DC isolator, and it will have a switch fuse unit. That is optional. SFU, generally it will have a switch fuse unit, and you can have definitely there will be SPD. SPD is DC SPD, surge protection device. So then it goes to the inverter. Okay. From the inverter, it goes to the ACDB. There will be an ACDB where you have the AC, you have MCBs will be there, miniature circuit breakers will be there. Then you have the SPDs, AC SPDs will be there. From there, it goes to the solar meter. Okay. Here the DCDB, here the ACDB. Before the inverter, you have a DCDB. After the inverter, you have a ACDB. ACDB, the same protection components there. You have the SPD and AC isolator. Then it will go to the solar meter. Solar meter means it's an energy meter. It measures whatever we generate from the solar power. So solar meter need not be a import-export meter. It can be what you call just import kind of meter. It measures whatever we generate. Then the solar meter, it goes to the what you call the main supply point, and it goes to the there will be a net meter here. It's not shown here. So here we will have 2 meters according to the conventions in Kerala, according to the regulations of KCRC and insistence of KCB. We have a solar meter and a net meter. Just remember that. Solar meter will measure the generated power. Your net meter will measure the import and export. Then it will go to the your power grid. Okay, so this will go to the power grid. So whatever is exported this is the last point. The net meter will be the last point. From the solar meter, it connects to the grid, your local grid. Then it goes to the net meter, and from the net meter you can measure the import. At the same time, you can measure the export. So you can get the net. If you have any doubt, please be free to ask the question, because don't be complicated by this. I will just repeat it for students. You have a solar panel. It will be arranged in strings based on your capacity. It can be 3 kilowatt, 2 kilowatt, 5 kilowatt, based on your home needs. In industry, it will be huge. Then you have different kinds of strings. Strings means nothing but a number of modules in series. We call it a string. So this string will be configured based upon the input characteristics of your inverter. Your inverter will have a input characteristic like maximum input current, maximum input voltage kind of data sheet is there. So you look at the data sheets, you can get the maximum input current, maximum input voltage. Based upon that, you make series parallel combinations of your solar modules. A number of strings will be defined based upon that. You add modules in series to make that particular voltage, which is below to the input requirement of inverter, or we don't need to cross that input characteristics of inverter. Then we make this arrangement of series parallel arrangement of this deployment of solar panels, and from this solar array we will get the power, DC power. It comes to the DCDB. In the DCDB, there will be in bigger power plants there will be string combiner boxes. For example, in Kudalmandam, before DCDB, you have a lot of string combiner boxes, like where the strings will be combined. In utility, in small power plants, you have a DCDB. DCDB, there will be DC isolator, there will be DC SPD, and you have SFU. Then you have the inverter. From the inverter, the conversion happens. Then it goes to the ACDB, where you have the AC SPD and AC isolator or MCB. Then it goes to the net meter, solar meter, where it measures whatever we generate. Fine. Then it goes to it's connected to the grid. Then it goes to the grid, to the power grids. In between, before that, we have the net meter, which is the import-export meter. It measures the import at the same time it exports. For example, at home, I have a 5 kilowatt peak solar power plant, which generates more power than what I consume. If I have an EV, electric vehicle only, I can offset it to some extent. So I installed it. If I can purchase an EV in a couple of years, that makes sense. Otherwise, I'm exporting a huge power to the KCB. Okay. And coming to the off-grid. Off-grid, we already discussed. Off-grid solar power plants, of course, you have a battery. That is a major component. And you have an inverter. And which will power your homes. See, this charge controller, it can be a separate component, or it will be integrated into the inverter. Just remember this. In the off-grid system, you have a separate charge controller or a charge controller which is integrated to the inverter. Here, there is a separate charge controller in this block diagram. The only thing is you have to, this is a bit complicated than the grid connected inverter. Whenever you design, I'm not going to take a class on design. When you design a off-grid power plant, it's very important that you have to have a profile of your load, a profile of your usage. So you define your inverter based upon your connected load. See, whatever the load you wanted to connect, if you wanted to switch on all your loads, then the inverter should handle it. The rule of thumb is 1.5 times of the connected load, which is the international way. But you can have double the size based upon, for example, you have more inductive loads, lot of fans, AC is available. Then, of course, you have to design your can be on 1.5 times or more. Better that you have more so that it can handle it. If you have an old AC or fan, what you call fan or fridge, better you replace it to conserve the energy. That is the advice from us. So there will be issues if you have huge inductive loads. So that is very important. So your connected load is it's a criteria for designing your inverter capacity. Okay. And your charge controller current can be also designed based on 1.5 times of whatever coming string current coming or whatever solar array current coming. It can be above that also, but we need to take care of all the extra current coming up due to surge and all. So I'm not going much into that. So your battery capacity, I already spoke to you. Battery capacity is based upon your needs. It can be something for one-day autonomy. That means a single day, 6 hours of solar power can charge it. And if you are sufficient with that, it's okay. And for remote systems, we generally design for 2-day autonomy or 3-day autonomy based on our requirement or site's requirement. So note these points for off-grid solar power plants. When you design for urban needs, we generally go for single-day autonomy. Okay. I'm not detailing on depth of discharge, the state of charge of batteries. You can listen all this stuff from different technical seminars. Even PES is actually holding international seminars every month. The previous month, there was a very good session on battery storage. So I request all the students to listen to that. In all the societies are doing this. And looking at inverters, actually, you have string inverters. Basically, string inverters we use in house. You have multi-string inverters. You have central inverters. you have what you call central inverters are inverters which are installed in Kudalmandam kind of solar power plants. Like we have huge plants which are installed there, where what you call the central inverters will be there. For example, in Kudalmandam we have huge 1 megawatt inverter, 2 numbers. But in plants like Fatilda in Rajasthan, you have even 5 megawatt inverters. So all the major manufacturers are producing huge inverters tuned to the capacity is 5 megawatts, individual 5 megawatt. So string inverters, I already explained, you can have multi-string inverters, and there are micro inverters available. You know about one company called Enphase. Enphase is a they have a micro inverter. It's available in the market and it is there. You have a lot of more than I guess more than 100 installations in Kerala itself. Micro inverters is simple. Each PV module will have a micro inverter connected, immediately converting that into AC. So you have only wires with AC running around instead of DC cables. So that way it is more safe. You have DC cables running around to the combiner box instead of DC cables running around. It's more safer. Only thing is a bit costly when compared to the conventional string inverters. There are a lot of certifications for grid-connected inverters. I am not detailing on certifications, just understand about 2 certifications not listed here. It is only 6 IEC, these are IEC certifications, International Electrotechnical Commission certifications. So whenever we go for grid-connected inverters, I remember the days when I designed a solar power plant for Kerala University 8 years back. We insisted on these 2 IEC certifications, which are not listed here. That is actually based upon our IEEE standard, IEEE 1547. See how IEEE is helping the global community. IEEE only developed IEEE 1547 standard, which is the basic standard utilized for developing IEC standards. So this is the basic standard, IEC 1547. UL has an equivalent standard 1741. And IEEE 1547, based on this, we have IEC 62116 anti-yielding standard, and IEC 62116 is anti-yielding standard, and IEC 61727 is inverter connected to the parallel grid. This is another standard. So these are the basic standards. We use it while we tender. Okay. And other standards, harmonics, you have IEEE standards of 519. So for addressing the harmonics, actually, we have a lot of IEC certifications. We insist. We have to prevent DC injections, and we have to keep the frequency. All this stuff will be addressed by the IEC 61727, I told you. So IEC 61727, IEEE, IEC 62116, these are basic standards for grid connected inverters. I'm not delaying that. And the net metering part. Net metering part is, as you know, I already explained just before going to the local grid, there will be a net meter which measures the import and export. Okay. So you have different companies like Secure, L&T offering net meters. I remember we have a Secure model import-export meter installed in Kerala University. A lot of L&T inverters are also there. A lot of international models are there, makes are there. And coming to PV technologies, of course, you know, this is a picture I took from the my Kerala University project. The first of its kind in Kerala, the largest 8 years back in ANERT, back developed by ANERT. So we used polycrystalline. These are crystalline silicon PV modules. These are polycrystalline PV modules. So in the first generation, you have monocrystalline and polycrystalline. Theoretically, the efficiency can be for monocrystalline up to 22 to 26% theoretically. So in practical, it can be up to 22%. In monocrystalline, polycrystalline up to 17% only. So yeah, this is more correct figures. You have monocrystalline PV modules. Looks like this. This is polycrystalline PV modules. You have 15 to 17%. It's not much available in the market now. It was flooded. Market was flooded with the polycrystalline from 2005 onwards, up to 2014 or 15, maybe up to 17. So after 17, we don't have polycrystalline PV modules available that much when compared to monocrystalline. So the whole manufacturing now shifted to monocrystalline. Monocrystalline also a lot of newer versions coming, up to 22% of efficiency. You have thin film PV modules, which is basically what do you call it? It is deposited on a substrate. It can be a flexible substrate, such as glass, metal, and plastic. The efficiency has a limit to 6 to 7% for amorphous. For cadmium telluride, a kind of thin film, it can be up to more than 12%. This is a sample amorphous silicon thin film solar PV installation on top of ANERT on our rooftop. And there are different versions with the different materials, like cadmium telluride is a First Solar. First Solar is a big corporation. They installed in Charanka, Gujarat also. It's cadmium telluride. You have copper, indium, gallium selenide, CIGS. You have gallium arsenide. These are commercial cells, commercial thin film cells. And you have a lot of innovations coming up. You can have half cuts to make it more cells placed on the available area, getting more generation. And you have PERC, passive emitter, and rear cell, where you have a passivation layer on the back side, on the rear surface, not back side, on the rear surface, that it reflects light back to generate more power, to allow more power. It is not bifacial. Bifacial is different. This is PERC. Generally, mono PERC is coming up. Monocrystalline PERC modules, which is so much abundant now in the market. If you call a vendor, just insist mono PERC. If you go for monocrystalline PV modules, because mono PERC is now already become cheap, less than 20 rupees per watt peak. Remember, more than 400 rupees per watt peak when I installed in Wayanad in Pakam. When I started my presentation, I was telling about Pakam tribal colony. It was more than 400 rupees per watt peak. Now it has come down to 17 to 20 rupees per watt peak. So that is the attraction. Bifacial. So on both sides you can generate. It's bulky. You need more space on this. You have 11 to 12% extra generation. I request the student community to experiment on all these technologies, get funding from chapters, societies, from IEEE. Go for smaller installations. I can guide you based upon your time. You have a lot of experience faculty like Dr. Bijana ma'am, who are all into renewables, who can guide you. So develop smaller projects in your colleges. Heterojunction technologies, actually it's a combination of different technologies. It can be crystalline silicon, amorphous thin film silicon together. So it's a bit costly, but very higher efficiency. You're getting more than 26. I've seen a lot of journal purpose illustrating some of the installations with very high efficient solar modules. I'm not going into details. You know about, if you look at a solar PV module nameplate, you have all the characteristics there. If you look at the electrical characteristics, nameplate, you have a power rating. It's a very small, old PV module data sheet. I'll just stop within 5 minutes. I think I have taken more time than allotted. So you have short circuit current, you have open circuit voltage, you have maximum power and voltage at maximum power and current at maximum power. So you have VMP, IMP, VOC, ISC. Please remember these terms. VOC is nothing but open circuit voltage. ISC is short circuit current. So open circuit is the largest voltage, no? Because if you open circuit it, there will be bigger voltage. That is the top peak voltage. Short circuit current is, if you short circuit, you have the highest current. So IV curve is nothing but like this. If you go for an IV curve, it starts from short circuit current, no? It's the highest current. If you short circuit, you have current here. Then you will have the open circuit voltage. It looks like it. You can see if you have more square kind of IV curve, then you have better solar PV module. The squareness of PV module is very important. So this is a maximum power point. It is power versus voltage. So if the squareness is more, then you have maximum better solar PV module. The squareness indicates the fill factor. If you divide VMP IMP by, that means maximum voltage and maximum current during maximum power divided by short circuit current into short circuit voltage, you will be getting the fill factor. Fill factor is almost 1. It is above 90%. You can see that it is a very good solar PV module. I remember I did some experiment on MATLAB Simulink during my MTech to make something like an experimental measurement to measure the quality of PV module on site. That was my MTech project. So fill factor is a very good indicator. You have temperature versus PV cell performance. You know, all the PV modules have a negative temperature coefficient of resistance. Crystalline PV modules are having more intensity on that, decreasing maximum power point. No, you can see the decreasing maximum power point when the temperature goes higher. 75 degrees centigrade, you have decrease in maximum power point. So that decrease is more reflected in voltage, not in current. Current is a little bit becomes higher, but because of this voltage reduction, ultimately the decrease of maximum power point happens. It is more good or better for a thin film. It's a better kind of like, it won't much vary, or of course it will vary, but when you compare with the crystalline solar PV modules, it's better. So in higher ambient temperatures, that's why the thin film PV module is suggested. And you look at the solar irradiation and how the IV curve is going. So IV curve is actually coming down here. Like if you have higher insolation, your irradiation is higher, you have higher currents. Okay, this way the IV curve is changing. And if you have the STG and NOCT, STG is nothing but the standard test conditions. And NOCT is a nominal orbital operation cell temperature, NOCT. You have ambient temperature 20 degrees centigrade, irradiance 800 watt per meter square, and mean speed 1 meter per second. All Europeans put these standards, not our standard. So cell temperature is 25 degrees centigrade, air mass 1.5. And one thing is missing here. What is missing here is 1000 watt per meter square. So you have 1000 watt per meter square, cell temperature of 25 degrees, not ambient temperature, just not the point. It is cell temperature, it's not ambient temperature. Back surface temperature is 25 degrees centigrade and air mass 1.5. is the air mass is nothing. Other things you are familiar, no? Your your cell temperature is back surface temperature is 25 degrees centigrade. For example, if you have a ambient temperature of 30 degrees centigrade, your cell temperature will become 40 degrees centigrade. So that's why in Kerala kind of atmosphere, in summer, you will get 85 to 90% of what you call output. For a 100 kilowatt plant, you can get 90 kilowatts. It is just because of the temperature loss. So because it is defined for 25 degrees centigrade. Instead, in real situation, it works for 40 degrees centigrade. In our normal 30-degree ambient temperature. I think you got it, what I am telling. All of a sudden, no, I couldn't, put all this stuff together to you. But I guess this will give you a spark to go for further studies. So I'll just look at some slides and just stop. I have a lot of slides again. So we put a tilt to the PV module. Why we are putting the tilt? This will explain. So see, if you make it flat, you cannot get all the rays falling on it. No, you have some rays come outside of it. So if you make it like a little bit tilted, all the sun, because the sun is for our northern hemisphere, for Kerala or the countries or states like this, we have sun on the south most of the time. So we make a general tilt of equal to the latitude. For example, we have a latitude 9 degree to 11 degrees in Kerala. So we orient our PV modules towards south, and we have a tilt of equal to the latitude. For example, for fixed tilt, we will select the latitude degree and make it that tilt. In Hyderabad, we will make a tilt of 15 degree. In Gujarat, we will go for a 20-25 degree tilt. So if you don't make a tilt of 20 degrees in Kerala, it is not efficient. Okay, I have seen a lot of installations with 20 degree tilt. It's not good. Okay. So, so as a compromise, we will make a tilt which is equal to the latitude. Okay. Some of the plants, Kerala University plants, I told you about, we installed it 7-8 years back with a German inverter. That's why it's working perfectly. This is a single day generation. I told you about a single day generation. Yeah, I'll finish within 2 minutes. So this is actually the watt per meter square curve. This is the kilowatt hour curve. The kilowatt hour curve follows the watt per meter square. A single day generation. This is the cow daily generation we are getting. I'll show some more pictures. The 200 kilowatt installed under consultancy by me and my team on behalf of ANERT. You can see Vadakanatha temple here. You can see the church here. It is in Thrissur Corporation. There's another picture. It's equivalent to saving. See what is the environmental effect of a solar power plant. For a typical small rooftop, 200 kilowatt, you have GHG reduction of greenhouse gas reduction of 340 tons. You have 62 cars. It's equivalent to 62 cars not used in a year. 88 barrels of crude oil not consumed. It's equivalent to 7 acres of forest absorbing carbon. Okay. And I will give a picture of our solar power plant installed in Kudalmangam. Yeah. Our pictures of solar power plant in Kudalmangam. Floating solar columns, I already explained. This is the hybrid plant and installation. I visited. It's a RE microgrid powering remote clinic in Babati, Arusha, Tanzania. So I think something is hanging. It's a hybrid plant. It has got a solar PV and a wind installation. Such. A little bit of hanging in my computer. Okay. So with that, I just finished this. I took more than the allotted time. Thank you for taking your time to hear me. Thank you so much. You can have a Q&A. Can you hear me?